Okay, so this is the second part of 11e. So let's just begin. So the equivalence, if these two statements are identical, then, so here we have an identity. So they have to be identical. We have ax squared here, we have ax squared. A has to be 2 because you have two lots of x squared here on the right. So that's the coefficient of x squared is 2, which means the coefficient of the x squared here must also be 2, so therefore the a has to equal 2. And the same is true for b. If we know what b is with this identity, we have b here is the coefficient of x. So we have b lots of x's here, but here on the left hand side we have 3 lots of x's, so therefore the b has to be equivalent to 3. And we're going to be using that idea later on. Let's try it here with these two vectors which are equal. These two vectors are equal, and it's just in terms of i's and j's. So the same number of i's on the left must equal the same number of i's on the right, and the same number of j's on the left must equal the same number of j's on the right as well. So just looking at the i's, we just consider the i's for a moment. On the left we have 5 of them, and that has to be equal to the number of i's on the right. On the right we have negative q plus 2 of them, so that has to be true. On the left, if we consider now the coefficients of the j's, so how many j's do I have? I have p, and on the right we have 11. So p equals 11, and 5 is equal to negative q plus 2. And from here, I could work out what I can work out what q is, because just continuing here, that means that 5 is equal to negative q plus 2. And then when you rearrange and make q the subject, you end up with the fact that q is equal to negative 3. No, that's not right. No, q is not negative 3. Q would end up being 3. No, that's right. Sorry, that's a mistake. No, q is negative 3. Q ends up being negative 3 then when you solve it. So, let's have a look at this question here. Now, OACB is a parallelogram, all there. O to A is A and O to B is B, so let's add that in. O to A is A, O to B is B. The diagonals OC and AB intersect each other at X. So, these diagonals intersect each other at X. We need to prove that the diagonals bisect each other. That means we're proving that these diagonals, these blue lines that I've drawn, cut each other in half. That's what bisecting means. And whilst we may know that as a property of a parallelogram that they do, we are being asked to prove it. So we can't assume that we know it's halfway. We have to prove that it is halfway. So there's a little hint here with a help. And it says try to find two vectors which do the exact same path but in different ways and make them equal to each other, make them equivalent. So what we're going to do is we're going to find 2 ways to get to x from the same point. I'm going to start from the origin. So I'm going to go from the origin to this point here, but I'm going to go 2 different routes. But it's not just any 2 different routes. You have to go 2 routes that don't go along the same diagonal, the bit that I don't know, because I don't know that this is half of the whole thing. Okay, so I'm going to go along that way, and that red bit there goes a part of that diagonal, and I have to go another way but not along the same diagonal. So I'm going to go along here, up there, no I'm not, well yes I am, and down there. I could do that. I'm actually just deciding I'm going to go a different way along the diagonal. I'm just going to go simply along there to get from O to X. So the red one goes from O to X and the green one goes from O to X. So I have 2 different routes taking me to the same place, and it goes along different diagonals to get to there. So the red one O to X is going to be O to A and then down from A to X. Now O to A is A to X. Well, A to X is we know it should be half of A to B, but we can't say it's half A to B because that's what we're being asked to prove. So it is some fraction of a to b, and that fraction I'm going to call lambda, some number of ab. So lambda lots of ab. Now, we got a, we have lambda. A to b, well, there's another way I can describe a to b. To get from a to b, I can go down along there and then across there. And that's what I'm going to do. A to b, this one here, is going to be minus a plus b. So I'm just going to tidy this up. So we have an a, our minus lambda a, plus b. That is O to x. So that's the red root. The green root, I'm going to write in that green. O to x is just going from here to here, going along there. Well, that is a fraction of the whole journey of O to C. Now, I don't know, I mean, I know it should be a half, but I'm not allowed to quote a half because I'm being asked to prove it. So I'm going to call it, it's some sort of amount of O to C. And I'm not going to use lambda. I'm going to use mu. If I can write it properly. There you go. So, it is mu lots of O to C. Now, O to C, I'm just going to go along there and then up there. And because it's a parallelogram, this one here is also A. Same as that one. So, O to C is B plus A. And if I expand this out and just write it in alphabetical order, I have mu A plus mu B. And what I have here now are two expressions for how to get from O to X along different diagonals. And because they are both expressing O to X, that therefore means that these two are equivalent. So therefore, A plus lambda A plus B is equal to mu A plus mu B. And I can just have a look, I can look at the A's on the left. I mean, on the left, I guess if I just tidied it up and rewrote it slightly differently, just factorize out the A's. I have 1 plus lambda A when I factorize it out of those two, plus B, so just make it more obvious. So the A's, on the left I have 1 plus lambda lots, and on the right here I just have mu lots. When I compare the number of B's to each other, it has to be the same because they're both these are describing the same starting point and end point, O to X. On the left I have just one B, so the coefficient of B is 1, an invisible 1 there. And on the right I have mu B. So we know that straight away that 1 is mu. Now that's not going to be true because I've obviously made a mistake. So I've just spotted my mistake. It's here. You probably spotted it as well. When I expanded this bracket out, I'm missing a lambda here. It should be lambda B. So let me just fix that. Now these two statements are equal, so let me just rewrite them. So we have A minus lambda A plus lambda B is equal to mu A plus mu B. Just to make it a bit more obvious, like I did before, that's 1 minus lambda a, factorising out the a. And because these represent, like I said, the same journey of O to x, then we can say that we should have the same number of a's on the left and right. So equating the coefficients of a, we have 1 minus lambda on the left, and that has to equal mu a's on the right. Equating coefficients of b, so how many b's do I have there on the left? Lambda, and on the right I have mu. And so I can work out what, this is basically simultaneous equations. So just looking at different ways you can do this. I can substitute one into the other. I'm just going to add these two together. No, whichever way you want to do it. I call that number 1 and I call that number 2. We're just going to sub number 2 into number 1. So we get 1 minus lambda is equal to lambda instead of a mu, because mu is equal to lambda. Write a lambda there. Which means we have 1 is equal to 2 lambda divided by 2. Therefore, lambda is equal to a half. And because lambda is a half, that means mu is also equal to a half. So that implies that mu equals a half as well. And we've shown that lambda and mu are both halves. Now, how does that help me? Well, because we said here lambda, lots of AB. A to B was that full diagonal. We wanted A to X, and we said it's equivalent to lambda lots of A to B. And so it's so that we're saying there, actually, that's a half of AB is equal to A to X. So it is the midpoint of that diagonal. Now, because the question was saying we're bisecting each line, we need to prove it's the midpoint of the other one. And here we said O to X was some sort of multiple of O to C, and we've shown that actually it's a half of it is what makes it work. So we finish up by writing here that therefore X is halfway along OC and halfway along the other one. I forgot what the other diagonal was, so halfway along OC and halfway along AB. And therefore the diagonals do bisect each other. Done. Okay, next one. This one here, we're told this is a parallelogram. We're told that O to A is A, O to B is B, and O to Q is a third A. So O to Q, and that bit there is a third of A. But we can also know that O to A is a whole A, so this second part has to be 2/3 of A. And we're told that O to B is B. So going from O to B is B. We need to find the ratio of O to X to X to C. So the ratio of O to X and X to C. Now, previously we saw diagonals were a half here, and we're going to use a very similar method to the previous one to see what they are, what our lambdas and mu's will be. They won't be a half, clearly, but we need to figure out what they are. So here's an explanation of what you need to do again. We're going to go to the same point, but via two different paths, is what this is trying to say. But we're going to make sure we don't go along the same diagonal. It has to be different diagonals that you travel to get to that point there. So we're going to write two statements to get from O to X. So the first one, I'm literally going to try and go from there to there. Right, so I'm going to go along this diagonal. The other one, I am going to try and use this diagonal instead. So I'm going to go along there and then down that way. So that's what I'm going to try and do. So let me do the blue one first. So my O to X along the blue. So going to the same point along two different routes but using two different diagonals. O to X, well, O to X is a fraction of O to C. So I'm going to call it lambda OC. Now, O to C, well, it's just a B plus a full 1A, because that there is equivalent to those two together to give me 1A. So it's going to be lambda of B plus A, which is just a lambda A plus a lambda B. The other root is that red one. So going from O to X, I'm going to go O to Q plus Q to X. O to Q is nice and easy, that's just a third A. Q to X, I have no idea what that is, but it is a fraction of Q to B. So I'm going to call that fraction mu. So we have still a third A plus this mu of Q to B. Now Q to B, there's lots of different routes I can go. I could go along there, down there, along there. But I'm going to go the other way. I'm going to go along that one and down there to get from Q to B, which we can see is negative a third A plus a B. So Q to B, that bit there, is negative a third A plus a B. And going along there, down there, and there, then going left along that one, last one, would give me the same thing when I simplified it. Tidying this up, we have a third A minus a third mu A plus mu B. Now, because we now have two statements that are both O to X, I know that these two have to be equal to each other. So we have, therefore, lambda A plus lambda B has to be the same as a third of A minus a third mu A plus mu B. And because they're the same journey, it has to be the same number of A's. Now, just make it easier to spot, I'm going to factorize the A out here. And we know the same number of A's. So on the left I have lambda A's. On the right I have a third minus a third mu lots of A. In terms of the B's, on the left I have lambda B's. And over here I have just mu lots of B. So I can solve these simultaneously. I'm going to do it by substitution. So I'm going to substitute in number 2 into 1. So I end up with mu instead of the lambda is equal to a third minus a third mu. I'm just going to times by 3 just to make it, rather than dealing with fractions, get rid of the denominators. So I get 3 mu is equal to 1 minus just a 1 mu. So mu, add mu to both sides. So 4 mu is equal to 1. Divide by 4. Mu is equal to a quarter. And because from here, I'm solving simultaneously, so I work it out, but I work out the other one, lambda is also a quarter. So that implies that lambda is a quarter. Now, the question asked me, find the ratio of O to x and x to c. Now, I used my lambda here. I said O to x was equivalent to a fraction of O to c. Now, I know that's a quarter, so I know it's a quarter of O to c. That O to x is a quarter of O to c. So this here, the bit I've just rubbed out, that there is a quarter of O to c. So I know that's just 1 part compared to 3 parts. And that's answering my question, because I want to know how O to x is in comparison to x to c. Well, O to x is 1 part and x to c is 3 parts. The mu, which I worked out, which was also a quarter, well, I used it here to work out what q to x was. I knew it was a fraction of q to b. Apparently it's a quarter of q to b. So q to x is a quarter of q to b. So I know that that is 1 part compared to 3 parts there as well. But I don't need these two, because I'm only interested in the ratio of O to x to c. So I'm going to answer it over here. O to x in the x to c. Well, that's in the ratio 1, 2, 3. And there you go. That is exercise 11E